So we're going to start today, like we often start. We're going to start with the problem from last time. Now, at the end of last time, we put up on the board and said, hey, there's these third-order Taylor polynomials, and we're not going to expect you to memorize these formulas. But we want you to understand what they are. So this is a problem from a review from last semester. Suppose you have g of xy, which is 7 plus x plus 3y squared plus 4xy plus 6x cubed plus xy squared minus 5x squared y, and is the third order Taylor polynomial to f of xy. And whenever I have a Taylor polynomial, I have the function, but there's also something else. It's where am I approximating the function? Because Taylor polynomials are approximations. So this is an approximation, g of xy to f of xy at a point, and we call it where it's centered. So centered at 2, 1. Which is to say that g of xy is a fantastic approximation to f of xy at 2, 1. And a very good approximation near 2, 1. So the question says, use this to determine all the second order derivatives for f of xy at 2, 1. Now, what's sort of the key to this problem? And why do we feel that this is fair? Well, the key here is you just have to understand one philosophy. And this is testing you to understand, to make sure you know that. So what's the philosophy? It says that Taylor polynomials match derivatives up to the order. That's what this is testing. So that's why these are actually good approximations, because they're mimicking the function in the lower order derivatives. And the lower order derivatives help determine behavior nearby, up to, we should just say up to the order. So the fact that we have it as the third order Taylor polynomial means that if I were to look at the function f of xy and look at all the derivatives up through the third order at the point 2, 1, compare f of xy and g of xy, they'd be identical. So what this happens to be is we can say the following: because g of xy is the Taylor polynomial, we can actually cross out f of xy and write g of xy here instead. That's the moral here, is understanding that, lo and behold, because I know that this Taylor polynomial is approximating, I can use it as a stand-in, as a substitute. So now the problem becomes very straightforward. It says, okay, I just have to find all these various derivatives. Well, good practice. We're going to be doing a lot of derivatives today. So we have our function. I'll just write it down again for reference. 7 plus x plus 3y squared plus 4xy plus 6x cubed plus xy squared minus 5x squared y. And then we just start working our way through derivatives. If we want the second derivatives, which we want because it says second order, start with the first order. G sub x. Okay, so what is g sub x? Help me out. 1. 4y. 18x squared. Y squared. Negative 10xy. Okay, g sub y. What will that be? So again, I'm going through here. 6y. 4x. 2xy, negative 5x squared. All right, g sub xx. So that means take the derivative of x and then take that derivative with respect to x. What do we get? Yep, that's the first term. Minus 10y. G, x, y. Well, then I can either take the derivative of x with respect to y, or take the derivative of y with respect to x. Well, let's take the derivative of x with respect to y. 4, 2y, and negative 10x. And g, y, y. Okay, so I'm going through g sub y. I'm looking for any of the y's. 6. And there's a 2x. Okay. Now again, these are the derivatives for the g function So it's not that the derivatives of g match the derivatives of f, it's that derivatives of g evaluated at the point 2, 1 match the derivatives of f evaluated at the point 2, 1. So what we need to do to finish is now evaluate. And the good news is that most of these terms have disappeared. So we're going to plug in x equals 2. 36 times 2 is 72. Y equals 1 minus 10. 72 minus 10 is 62. Gxy at 2, 1. Well, we're going to get 4 plus 2 more. That makes 6. Then we're going to subtract 20. So negative 14. And gy, y at 2, 1. Well, we're going to get 6 plus 2 times 2, makes 6 plus 4, which is 10. And that's the answer. All right. Good. Well, now on to today. And if you like taking lots of derivatives, today's a good day, because we're going to do lots of derivatives. We're starting in sort of a 3-day phase, where we're going to look at various themes. Well, one big theme, variations on that theme. So what we're going to be talking about over the next couple of days is optimization. Now, what is optimization? Well, I like to say optimization is the est part of calculus. In other words, you're looking for things like the biggest, the shortest, the tallest, largest, smallest, cheapest, fastest, slowest. What we're trying to do is we're trying to say, I want to do the most extreme I can. All right. So when we're talking about this, we're looking for maximums and minimums. So we want to make sure we understand what things are. So we'll say a function has a local maximum at a point f of ab, at a point ab, if f of ab is bigger than f of xy if I'm near ab. So in other words, what you should be thinking here is, So what's our picture? So we have our space, our x, y, z space, and here's a point A, B, and what happens is I plug it in so that up here, this height value, this is at f of a comma b, and what we want to be true is we want to say we're a maximum if essentially everything around us is below us. Now when I say around us, I really do mean very nearby. So there's a key word here, near. The question is, how near? Within a millionth. That's all I care about. Or even less than that. Just some small neighborhood. Okay, so that's a local maximum. A similar idea is a local minimum says that I'm smaller than anything nearby. Okay, so that's a local max and a local min. So, what are the other things we could do? Well, there's something called a global max, and a global max removes the condition about being near. It says, look, I'm just bigger than everything. Doesn't matter what you plug in, I'm bigger than. Well, technically, bigger than or equal to. And similarly, global minimum says, I'm less than or equal to any point you could plug in, anywhere around. All right. So we're looking for maxes and mins, and there's the two flavors. There's the local variety, and then there's the global variety. And we're going to go through and do both of these. Today we're going to be focusing more on the local behavior. Now the question is, where can they occur? So let's recall something. We're going to start with the gradient. And the gradient has this really cool property. And it says that, the gradient says, if you follow the gradient, you're going to go up in the steepest direction you can. In other words, it points in the direction of maximum increase. Negative the gradient, that points in the direction of greatest decrease. Well, why is that helpful? Well, suppose I'm at a point, and let's suppose I have a gradient and it's not 0. Can I go up? If I can, how do I do it? Yeah. So if the gradient says this way you go up, you move a little bit. Just a little bit. That's okay. What if I want to go down? I back it up. Opposite the gradient. So when I have a gradient, and when it exists, and when that gradient isn't 0, and then there's one other thing. When I actually have the freedom to move, okay, so I have to be able to go forward or backwards. So I have to move with the gradient or against the gradient at some point. Then I can't be at a min or a max. Because to say you're at a min or a max says I can't get smaller when I'm at a minimum. If I'm at a max, I can't get larger. So this is wonderful because it tells us where we should focus our search. If we're looking for things which are the largest or the smallest that are possible, now we have some criteria. So we're going to focus our search on those points which are really critical to solving this problem. So we're going to call them the critical points. So critical points, what are they? Well, they are places where a min or a max can occur. And so there's 3 things we look for. The gradient being 0, the gradient being undefined, or the boundary. And of these, the big one we're going to focus on is where the gradient is 0. So I should say that most functions we're going to deal with are nice functions. We're going to avoid many cases where the gradient is undefined. The boundary cases, why is the boundary there? Well, remember we said we had to have the freedom to move. So it might be saying that the gradient might be pointing in a certain direction, saying go that way, and you'll go up. And we'll say, but we can't, because we're already on the edge. We can't move that direction. We're on the boundary. So that's why we have to include the boundary. So today we're not going to worry about these last 2. We will talk more about these over the next couple of days. But again, today, most we're going to talk about where the gradient is 0. We're going to call those the critical points. So let's do an example. Find all the critical points of the following function. 3x cubed plus y squared minus 9x plus 4y. So one thing we can see is that this has a nice derivative. Or we should say nice derivatives. Of course, it's multivariable because it's a polynomial. All polynomials have nice derivatives. They're very nice functions to work with. Also, there's no boundary because a boundary would be where you have your domain. And there's no restriction on our domain. We go on forever in all directions. So really, this truly is a case where we just need to look for where does the gradient equal 0. And of course, I should point out that this 0 is the 0 vector, not the number 0, which is why sometimes it's hard to see that's a bold 0. Well, so if I want to find where the gradient equals 0, what needs to be true? Each part of the gradient has to be 0. What's the gradient consist of? The partial derivatives. So really, what we need, when we say the gradient equals 0, that translates into saying that all the partial derivatives are 0. So that's what we think of. So let's take our f sub x. What do we get when we take the derivative with respect to x? 9x squared minus 9. We're going to set that equal to 0. F sub y. 2y plus 4. We're going to set that equal to 0. And now we have a system of 2 equations and 2 unknowns. Now this particular system of 2 equations and 2 unknowns is a very nice system of 2 equations and 2 unknowns. It's not so hard to solve. For example, let's start with the bottom equation. What does that tell you about y? Minus 2. Let's start now with the top. 9x squared minus 9. Well, you can simplify it to say x squared equals 1 because you can divide by 9, move the 1 across. So what is x? Yeah, x is plus or minus 1. And now we combine, so we end up with, there are actually 2 critical points. The plus 1 with the negative 2, and the minus 1 with the negative 2. And there you go. All right, well, that's not so bad. So now we can definitely we can find our critical points. Of course, we have the issue, what are they? So, we have to be a little bit careful here. It turns out that just because you're a critical point, it's not enough to guarantee you're a max or a min. So there's this example here. Here's this function, g of xy, which is x minus 2y times 2x minus y times x plus 2y times 2x plus y, which turns out to be 4x to the fourth minus 17x squared y squared plus 4y to the fourth if you multiply it out. Now I claim this has a critical point at the origin. Let's just do a quick check. What would g sub x be? 16x cubed, then minus 34xy squared, and g sub y, well, that'll be minus 34x squared y plus 16y cubed. And at the point 0, 0, what do you see? Well, because you see all those x's and y's, everything goes to 0. So at 0, 0, it's the case that the gradient of g does equal the 0 vector, which means that 0, 0 is a critical point. Now, is it a max or a min? Now, it might not be so obvious right away, so I happen to have plotted the picture, and let's take a second here. We'll deconstruct what's going on. So the edge here, you can see it's going up and down, and then up again, then down again, and on the backside, up on the backside, down on the backside, up and down. And you can see that in some directions, say along an axis, it looks like I'm at a minimum, because I sort of shallow out. But in other directions, say along the line x equals y, I look like I'm at a maximum. In fact, what you could do, there's this picture here on the right-hand side, which says, I can look at where is the function negative and where is the function positive. So the function being positive, that's like, for example, along the axes, you can see I'm coming up from 0, 0. But on different directions, like along the line x equals y, the function is negative, so I'm coming down from 0, 0. So I'm neither a max or a min. So, okay, we run into the same issue that we had in Calculus 1. We say, okay, so if we found the critical points, and now we want to figure out what kind of critical points they are. So do you remember what we did in Calculus 1? Yes? Okay, good. All right. There was a test. In fact, there were two tests. Do you remember what the first one was called? The first derivative test. Now, how does the first derivative test work? Well, you're thinking of another test. So the first derivative test says, look at the first derivative. And you're basically saying, let me look from two directions, from the left and from the right, and how is my function? Am I increasing or decreasing? Now, we have some bad news. In multivariable calculus, there's no first derivative test. Why not? Well, the problem is there's so many directions you could approach that just checking a couple of directions is not enough. Because I could set up and create a function where I could approach it from a million different directions, and every time I approach in those directions, it would look like I'm at a minimum, but then there's one direction where I could say, no, it thinks it's at a maximum. And so you cannot exhaustively check every direction in an efficient way using the first derivative test. So there's no first derivative test for multivariable functions. Well, we said there were two tests. So what was the name of the second test? Yeah, the second derivative test. So it turns out that there is a second derivative test. Now, someone mentioned concavity. That's what the second derivative test involved. It said, let's look at the concavity of the function. But actually, what was happening with the second derivative test, we'll pause for a second and have a Calc 1 flashback here. What's happening with the second derivative test, if you think about it, is it says your function f of x is, we'll think of it in terms of Calc Calc 2. Put on our Calc 2 hats, right? It's f of a plus f prime of a times x minus a plus f double prime of a over 2 x minus a squared plus dot dot dot. So our Calc 2 hat says, hey, that's a Taylor polynomial. So the second order test said, hey, I'm at a critical point, so that term goes away. And now what happens is that my local behavior is being dominated by this next term. So if the second derivative were positive, this looks like a parabola opening up. So if the second derivative were positive, I have that shape. And if the second derivative were negative, well, I'm going to look like a parabola opening down. And if the second derivative were 0, well, the problem then says that drops out. You have to move further down and look for your next terms. And so we said, look, if the second derivative is 0, we don't know what's going on. Now, the way I remember the second derivative test, and it's going to be useful here, I'll write it down, is with a series of pictures. If the second derivative is positive, our curve looks like that. If our second derivative is negative, our curve looks like that. And if our second derivative were 0, we have no idea what's going on. So, second derivative is positive, you're at a min. Second derivative is negative, you're at a max. Second derivative is 0, you don't know what's going on. All right, so this is our second derivative test. So it might be useful to remember that in the next few minutes. So we want to say, does something similar happen in Calc 3? And the answer is yes. Okay, so remember we talked about Taylor polynomials last time. And the reason we talked about it last time was we wanted to talk about what's the behavior going on today. So I'm at a critical point, so that f sub x and f sub y terms drop out. They're gone. So now I'm going to the second order terms, and we said, well, we have the f of ab term plus the second order term, and that, again, this is this matrix thing on the end. That's what's determining our behavior. And then we spent some time last time saying, hey, there's this really cool fact that we don't need to prove, but we said the following, that ABBC has this thing called eigenvalues attached to it, called lambda 1 and lambda 2. And if lambda 1 and lambda 2 were positive, then locally we're a minimum. And that's because when they're positive, our shape looks like sort of a three-dimensional parabola opening up. If lambda 1 and lambda 2 were negative, then it looks like a parabola that's opening down, which means that our point is at a maximum. If they had different signs, then what that means is in one direction, it looks like we're going up, and in a different direction, it looks like we're going down, and that was the shape that we called a saddle. And then, the last thing is one of them were 0, then we have no idea what's going on. So this should feel like, so this is really just a nice generalization of what we did with the second derivative test. Because we're saying, okay, let's look at our behavior from our second order terms. And it is. And so, we have the following. All right. So just remember that we have these two things called lambda 1, lambda 2, and this quantity is going to be important. So AC minus B squared. So for us, A is the fxx, C is the fyy, and B are these fxy and fyx terms. So we're going to be interested in that quantity, fxx at AB times fyy at AB minus fxy at AB squared. And now we have the second partials test. So it says the following. If we're at a critical point, so that means our gradient equals 0, compute this quantity we just talked about, fxx times fyy minus fxy squared. That's at, for those of you who've taken linear algebra, that's the determinant of the matrix. For those of you who are going to take linear algebra, that's the determinant of the matrix. Okay, good. Now there's a couple possibilities. If this quantity that we compute is negative, that means that those two numbers, that lambda 1 and lambda 2, were different signs. So that in one direction it looks like we're at a maximum, but in a different direction it looks like we're at a minimum. And so we call that a saddle. It says we're neither max nor min. If this quantity is positive, well, that says that lambda 1 times lambda 2 was a positive number. So they could both be positive, or they could both be negative. So at this point, we know we are at a max or at a min, but we don't have enough information to conclusively say which kind we're at. So how do we figure that out? Well, for that, we go a little bit further. So here's sort of the idea. So suppose I know that I'm at a place where the gradient equals 0, and I also know that d of AB is positive, which means I'm at a max or a min. So the idea is, look in the slice. What's happening? Well, that's actually saying it right here. If you look in the slice, the picture says that instead of having a three-dimensional thing, when we look in a slice, we're going to have a nice one-dimensional thing, just a curve. And if I'm a local max or a local min in 3 dimensions, I am still a local max or a local min in 2 dimensions. So back here in our old setting. So as a result, what we can do is we can say, let's go to our old setting. And in our old setting, we use just the second derivative test. So here, the second derivative, if I'm looking in a slice, could be fxx. Now that's if I look in a slice where I'm fixing my y value, and I take derivatives with respect to x. I could have just as easily looked in the fyy slice, because I just need to fix. I'm looking at a slice and saying, is it a max or a min? So that's what's going on. That's why we look in, say, is fxx positive or is fxx negative? And then it's just the same thing we had before, where if it's positive, then the curve is at a min, and if it's negative, the curve is at a max. And it definitely has to be one of those two. If we push down here, we can't have fxx be negative, or sorry, fxx be 0, excuse me. Now the last thing is, what happens if this value is 0? The test is inconclusive. And it's inconclusive for the same reason that it was before. The problem is that essentially the second order terms aren't governing your local behavior. That means you have to push and look in more terms. And we're not going to do that. That's not the goal of our class. Okay, well, that's the idea. That's the theory. Now, the practice, and a lot of practice. So find and classify the critical points of f of xy. So there's 2 steps. The find is what we'll do first. So the find is always the same thing. Set the gradient equal to 0, then solve. And what you'll do is we're only ever going to do this for functions of 2 variables. We are not ever going to talk about find and classify for functions with 3 variables. It's always going to be functions of 2 variables. So you're going to take 2 derivatives, derivative with respect to the first variable, derivative with respect to the second variable. We're usually going to have x and y's. It doesn't matter what we call them, but we're just going to take those 2 derivatives, set them equal to 0. In our case, what is f sub x? 2x minus 3y plus 1. Set that equal to 0. What is f sub y? Negative 3x plus 4y minus 1. We're going to set that equal to 0. So taking the gradient equals 0. Okay. That's just should be an automatic when you see something that says find and classify. If you see find and classify, set the gradient equals 0, automatic. You don't even think about that. Then it's like, okay, I have a system of 2 equations and 2 unknowns, and I try to solve. Now this one's more interesting than the one we had before, in that both of the equations involve x and y. But it's not so bad. So we start rearranging. Now, when you're solving systems of equations, there's just a handful of things you can do. So as a general guideline, what are things you should look for? I I would say look for things that can factor, and look for things you can substitute, and then, I don't know. That's pretty much my list. It's a very short list. I guess we'll say combine. After that, you start turning to religion and saying, please, Newton, I'm a good person. I've lived a good life. Please help me solve this. But no. Factor, substitute, that'll work. All right, well, okay, so we have two equations to us. What I like to do, because they're linear, I like to combine them together to cancel terms. So let's say I wanted to cancel the x terms. One way I could do it is if I said, well, let's make both the terms look like 6x. So if I multiplied the first equation by 3, that would be 6x minus 9y equals negative 3. So when I say multiply by 3, all the terms get multiplied by 3. Negative 6x plus 8y equals 2. So multiplying the second equation by 2. Add them together. What happens? The x's cancel by design. Negative 9y plus 8y is negative y. Negative 3 plus 2, negative 1. And now, lo and behold, we know y. Y equals 1. Okay, so that's y. Once you have y, getting x is not so bad. Plug it back into any of the equations you had before. So, for example, say the first equation. That becomes 2 minus 3 equals negative 1. Sorry, 2x minus 3 equals negative 1. And then that says that 2x equals positive 2, which means x equals 1. Which says that for our critical point, there's exactly one critical point, namely 1, 1. So it's a very short list of critical points. All right, that's it. So now we're done with stage 1. We've done the find. Now we go into stage 2, the classify. So you always find first, classify second. So for the classify, what do you do? Well, you come and you compute this value. So we're looking at fxx, fyy minus fxy squared. So that means we need to compute our second order derivatives. What is fxx? 2. What is fyy? 4. What is fxy? Negative 3. So it turns out that our value for D is 2 times 4 minus negative 3 squared. And be careful here. A lot of people will say, oh, negative 3 squared becomes negative 9. It's not. When you square the negative, it becomes positive. So what we're going to end up with is 8 minus 9, or negative 1. Now, you don't care about the size of the number. The size of the number is completely unimportant. What do you care about? The sign. We're going to see the sign. It's going to open up our eyes when we see the sign. It's negative. So, if it's negative, what does that mean? It means it's a saddle point. It means that there's two directions that have opposite behavior. So, our classification, so we found it, and the classification is it's a saddle. All right, so that's a good warm-up. Well, now let's do a few more. All right. For the function g of xy equals x minus y squared sine of x, show that 0, 1 is a critical point, and then classify it. So, let's, how do you show something as a critical point? You check the gradient. So for us, we say, okay, we want to find g sub x. Well, 1 minus, and then derivative of sine is cosine. So 1 minus y squared cosine of x, g sub y Well, the x term goes away. In fact, the only y there is the y squared minus 2y sine of x. So when we plug in 0, 1, g sub x at 0, 1, well, that's 1 minus 1 squared cosine of 0. But cosine of 0 is 1. So you end up with 1 minus a bunch of 1s multiplied together, which is 0. G sub y, well, that would be minus 2 times 1 times sine of 0. And sine of 0 is 0. Okay, so this is the show that it's a critical point. So we've now shown it's a critical point because the gradient equals 0. So the next thing we have to do is to classify. So we go into our second order derivatives. So gxx, what does that turn out to be? Y squared sine of x. Gxy, minus 2y times cosine of x. And gyy, negative 2 sine of x. So we want to look at gxx times gyy minus gxy squared. Well, plug in y equals 1, x equals 0. What happens to gxx? We get 0. Gyy? 0. It's going to be hard to recover from 0 times 0. Then we're going to subtract. What is gxy? Well, it's negative 2 times 1 times cosine of 0, which is negative 2. Because cosine of 0 is 1. So we end up with negative 4. Now what's true about negative 4? It's negative. In fact, we even said it. It's negative 4. So it's negative. Okay. So what kind of point do we have? Saddle. Now you're probably thinking, wow, 2 saddles in a row. Actually, saddles are very common. They're probably more common than maxes or mins. So it's not too surprising. What's the point of this example? The point of this example is you don't have to be a polynomial. Almost all the examples you'll see are polynomials, but you can have any function at all. But of course, when it comes to solving systems of equations, we're much better when it comes to polynomials. Okay. Now, the next one. Find and classify the critical points for, oh my goodness, this one looks a little bit more interesting. X to the fourth minus 4xy minus 7x squared plus 4y squared plus 4x minus 8y plus 20. So this was a problem that I wrote for an old final exam. And then the next semester, when I was not teaching the class, they were like, we love this problem so much, we're going to put it back on the final. So they did. And then a year later, again, I was not teaching, they said, oh, that was such a great problem. We're going to put it back on the final. So this problem is so nice, it's been used thrice on the final. But I should tell you, I'm not a big fan of recycling. So don't expect to see this on the final. You're going to get something always new and original because you're paying good money to learn calculus, so you should get your money's worth. Okay, so here we go. Let's now to flex our mathematical muscles. All right, what is g sub x? So we always start with the find first. You can't classify anything until you found them. So we find first. G sub x is 4x cubed minus 4y minus 14x plus 4. Now, already you should be feeling nervous because that looks harder than what we've done so far. Okay, but remember there's 2 derivatives. G sub y is negative 4x plus 8y minus 8. All right. So, what's our basic mindset? Well, our basic mindset is our 2 big tools are substitution and factoring. I always like to check factoring first. Can it factor? And if it can, do it. Now, when I see a cubed, I'm pretty much say, nope, not going to try for that one. That's tough. Cubes are tough, unless somehow we can factor an x out. And there's just nothing to factor down in the g sub y. So now I say, okay, what about substitution? Can we substitute? In other words, can we take one of these two equations and solve for a variable? Yeah. Notice in our second equation, there's only a single x and there's only a single y, which means that we can solve for either x or for y. Now, which one should we solve for, and why is it y? So which one should we solve for? We should definitely solve for the y. Okay, but why? Yeah, because notice there's an x cubed. You don't want to be cubing stuff. So you should not cube stuff. So we're like, okay, well, so I don't want to replace the x. So I want to replace the y instead. In fact, the only y that's up there is the 4y. So we can do something pretty simple here. So we can say the following. 8y, that's 4x plus 8. And I can even say 4y is 2x plus 4. And the reason I'm just going with the 4y is that's what I see. So now we substitute. So 4x cubed minus 2x plus 4 minus 14x plus 4 equals 0. Good news, there's only x's. Bad news, it's a cubic. Well, maybe it's not all bad news. Let's see what we have here. 4x cubed. Then we have minus 2x minus 14x is minus 16x. Minus 4 plus 4 is gone. That doesn't look so bad. Factor out of 4x. X squared minus 4. So what can we say about x? Zero. And then plus or minus 2. Because x squared minus 4, we could have even gone one step further and said this is 4x, x plus 2, x minus 2. But x squared minus 4, x squared equals 4. So plus 2, minus 2. Now, that's our x. We come back up here. Well, we probably should actually properly do this. So if we solve for this, that says y is equal to x plus 2 over 2. So divide both sides by 4. So when x equals 0, what is y? It'd be 1. 0 plus 2 over 2 is 1. When x equals 2, what is y? It's 2. And when x equals negative 2, what is y? 0. So these are our critical points. Okay, so we've done the find. Are we done? Well, with the find, we are. But now the classify. Okay, so here we go. For the classify, when we're classifying, after we've done the find, what's our next thing to do? Take the second derivatives, right? So, what is g sub xx? 12x squared minus 14. All right, what is gxy? Negative 4. What's gyy? 8. Okay, so we get that d, that's equal to 12x squared minus 14 times 8, subtract negative 4 squared, which is subtracting 16. So the nice thing is this only really depends on x. So suppose, well, let's go ahead and plug points in. So let's say we plug in x equals 0, y equals 1. Well, we're going to get negative 14 times 8, subtract 16. Now, do I know the value? No, I don't know the value. Could I find the value? Yeah, we could probably find it. It's 128. Negative. Do I care that it's negative 128? Well, I don't care about the 128. What do I care about? Yeah, negative. It's really easy to see it's negative because it's a negative number, subtract even more. So I just care about the fact that it's negative. So what does that tell us about 0, 1? It's a saddle point. Cool. Okay, now let's plug in 2, 2. All right, so we get 12 times 4. That's 48 subtract 14. 48 subtract 14, 34, I think. Yes, maybe?
Sure.
Okay.
You didn't multiply by the 8.
And then I multiply by the 8. Of course, in 34 times 8, that's 272, I think. Then we're going to subtract 16. Now, you might say, oh, we better compute this number. But really, you just look at it and say, 34 times 8, I bet you it's bigger than 16. It's true. It's true. So this is positive. Okay, so what do we know at this point? We know it's one of the things about either a local max or a local min. And I should emphasize local. Because, well, okay, I'll come back to why we should emphasize local in a minute. Okay, which one is it? How do we tell? Yeah, see, notice that GYY is really easy to compute the sign of GYY. It's positive. So the second derivative with respect to y is positive, so what kind of point is it? Max or min? It's a min. So if you're at a positive, you're a min. And again, this is a local min. When you plug in negative 2 comma 0, well, it turns out the only thing that matters is that x squared. It's going to turn out to be the same. So it's also a min. Because, again, this doesn't depend on x. And so there we go. All right, so there's our find and our classify. Now, why do we emphasize the word local? We should have talked about this here. Because it's not just a min or a max, it's a local min or a local max. The reason why we emphasize the word local is, where does this test come from? It comes from the idea of our approximation. And our approximation is only good nearby. So when we're using that Taylor polynomial, it only tells us what's happening very close by. So as soon as you move away, you have no clue what the function is doing, and therefore you have no idea what's going on in the global setting. So that's why when we use the second partials test, it's always going to be a local test. We might want to say, well, what if I want to find something, the absolute max or the absolute min, something global? Well, we'll talk about that next time. Well, let's do a little bit more practice. So we're going to do a few problems. And it's not like they're very different from each other, but you're going to see that they may look very distinct, but they all have the same sort of flow. So find and classify. So they all start the same way. They always start with find, which means we start by taking our partial derivatives. F sub x, in this case, 2xy plus 2x minus 6y minus 6. And then f sub y. Well, that's x squared minus 6x plus 2y plus 7. All right. Now we start to look for things we can do. Now there's lots of things you can think about doing. And this problem has a couple of options. One problem is, or rather one option, see that y there? It's a single y in that expression. If you have a single y, that says you can do a substitution. So I could solve for y, and then I could introduce y as a quadratic in terms of x, and I can substitute it in. And then I'll have a cubic. And, okay, try to solve a cubic. It's possible. Could work. But there's another option. Look a little bit more closely at what you have here in that first line. Remembering, we're going to set things equal to 0. So recall what we said. Look for factoring and look for substitution. Those are the two things to look for. And between these two options, you always want to try to go with factoring first. Factoring is such a powerful tool. So if you stare at this for a little bit, you say, hey, notice that the first two terms kind of feel like the last two terms. By that we mean, if you look at the first two terms, you could pull out 2x times y plus 1. And from the last two terms, you could pull out 6, and you'd have y plus 1. Which means this is really 2x minus 6 times y plus 1. Or, going a little bit further, 2 times x minus 3 times y plus 1. And remember that we always set the partial derivatives equal to 0. So our conclusion is that x is going to either equal 3 or y is going to equal negative 1. Well, that makes life pretty easy. So suppose we want to go down the x equals 3 route. What happens? Well, now you come into the f sub y, and you plug in 3. So we're going to get 9 minus 18 plus 2y plus 7 equals 0. So if we have 9 plus 7 minus 18, well, that's 16 minus 18. So that's minus 2 plus 2y equals 0, which tells us that y had better be 1. Giving us that one of our critical points is at 3, 1. So we're going to make a list. What if we had gone down the y equal negative 1 route? We'll come into here. Then if y equals negative 1, we're going to get x squared minus 6x, then minus 2 plus 7. That makes plus 5 equals 0. Now that factors. X minus 1, x minus 5. Which means that we get x equals 1 or 5. And now that gives us, again, some points. Namely 1, negative 1. So 1, negative 1, x, y. Or 5, negative 1. 5, negative 1. And now we've explored everything and we have our critical points. So we've done the find. Well, after you find, the next stage is to classify. So to classify, make sure you take your derivatives that you need. So we need to have our d, which is fxx times fyy minus fxy squared. Now one thing you can do is you can just do them right away. Put them in the same expression. So the derivative of f with respect to x would be 2y plus 2, and that's it. Derivative of f sub y with respect to y, well, would be 2. Then we're going to subtract f sub xy. So if we came here taking derivative with respect to y, we'd have a 2x and a minus 6. Now, of course, you'll see it's the same thing if we took f sub y, took derivative of that with respect to x, 2x minus 6. It's not a bad check to do things, and don't forget that's being squared. Now, this is a function of x and y, so we're going to plug all these in individually. So d, if I plug in 3, 1, well, that would be equal to, so 4 times 2 minus, and here I'm going to get 6 minus 6, which is 0, squared. That's 8, but I just care about the sign. That's positive. So that means it's a min or a max, and if I look at either the fxx or fyy term, they're positive. Positive, that means we are at a min. So 3, 1 is a local min. Okay, let's do another one. 1, negative 1. Well, in that case, we're going to get, for here, we're going to get 2 times negative 1 plus 2, which is 0, times 2 minus 2 minus 6, negative 4 squared. Well, look, it's really hard to recover from that 0. So that's negative 16, which is less than 0, which means when I see a negative number in this d term, that's a saddle. And you're going to see that we're going to get the same thing happening with 5, negative 1. Because we get negative 2 plus 2 again, 0 times 2. Here we get 10 minus 6, which is now positive 4 squared. Still negative 16, but still negative, and therefore also a saddle. And that's it. That's the classify. We went through each one of these points, and we figured out what happened. And now we're done with the problem. Find and classify. Good. Well, that was so fun. We'll do another one, right? Find and classify all of the critical points for h of xy which is equal to x cubed minus 3xy squared plus 2y cubed plus 6y squared minus 24y plus 42. Wow, what a mouthful. All right, can we do it? Well, we do what we always do when we do the find. We say, well, let's find h sub x. What is that? 3x squared minus 3y squared, and then nothing, 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 nothing. Well, that's pretty good. And now, what is h sub y? Probably a lot more. Nothing there. Well, there, minus 6xy plus 6y squared plus 12y, and minus 24, 42 goes away. Now, oftentimes when you're doing this, you say, okay, I need to set them equal to 0. It's often better to focus on one of them. And looking at these two terms, I would say that if I were going to focus on one of them, I want to focus on the h sub x. It has fewer parts. Fewer parts is usually easier to work with. And in fact, we can see a couple of things. 3 is common, so that becomes x squared minus y squared. Pull that out. And then it's like, oh, a square minus a square. Difference of squares. So we can write that as x minus y, x plus y. And so, our conclusion is that there's two possibilities. 1, x is equal to y, or 2, x is negative y. So let's suppose for a second, let's go with the x equal y first. Suppose x equals y. Then we come to our second piece. So we get minus 6 times y times y. So that's minus 6y squared plus 6y squared plus 12y minus 24 equals 0. Well, the minus 6y squareds cancel. 12y minus 24 says 12y equals 24, which says that y had better be 2. And if y is 2, x is y, that leads us to the point, we'll write it over here, 2, 2. Now let's go to our other option, which was x equals negative y. So here, the only thing is there's one x, so what happens? Well, previously it was minus 6y squared, but because of the negative, it becomes plus 6y squared. So 6y squared plus 6y squared plus 12y minus 24 equals 0. Or 12y squared plus 12y minus 24 equals 0. Everything has a 12 in it. Divide out. Y squared plus y minus 2 equals 0. And that looks like something we can factor. How? Well, y and y, two things have to multiply to negative 2, but add to plus 1. Well, plus 2 minus 1 do that. Check y squared, and you have a minus y plus 2y, which gets you plus y minus 2. Which tells us that here, y is either negative 2 or 1. Now, remember x is negative y. So if y is 1, x is negative of that, which means that we're at negative 1, positive 1. And if y is negative 2, x is negative negative 2, which means x is positive 2, and y is negative 2. So those are our 3 points. We've now done the find. All right, that's not so bad. What comes next? Well, now we move to classify. So we write down all our second order derivatives. hxx. Well, not so bad. 6x. hyy. What is that? Well, that's going to be a little bit longer. Minus 6x plus 12y plus 12. All right, good. And of course, hxy should be, come here, take derivative with respect to y, negative 6y. I get the same thing if I came and took the derivative with respect to x. So, we get that our d is 6x times negative 6x plus 12y plus 12 and minus negative 6y squared. So we plug in some values. 2 comma 2. Well, that's going to be 12. Then, if it's 2 comma 2, so it's minus 12 plus 24 plus 12. So that would be 24. And then we're going to subtract negative 12 squared. Well, 12 times 24 is definitely bigger than 12 times 12. So I don't know what this value is. It's 144. But it doesn't matter. I know it's positive, which means I'm at a min or a max. I see it's a positive value there, and therefore 2, 2 is, again, a local min. Don't worry, some problems do have local maxes. I don't know if any of these do, but some do. So don't always say, aha, it's always going to be a local min. No. Don't read too much into that. The problem is we like positive numbers in the leading coefficients, and they often determine behavior. Negative 1, positive 1. So that would be negative 6. And then here, we're going to get plus 6 plus 12 plus 12, which is 30. All right, and subtract, well, negative 6 squared. But we're toast. As soon as these have opposite sign, you're done. Because this is going to be a negative, and then you're subtracting. It's only going to get more negative, which means at this point, it's a saddle point. All right. How about 2, negative 2? Well, 2 times 6, that makes the first term 12. And then here we're going to get minus 12 plus minus 24, then plus a 12. So what do we have there? I have to do that again. Minus 12, minus 24, that's minus 36, plus 12 makes minus 24. And subtract positive 12 squared, because it's negative 6 times negative 2. But it doesn't matter. Again, these have different signs. You're done. You're done when you see those have different signs, because it's a negative, subtract something, it's even more negative. Very negative. Extra negative. So that means at this point, again, it's another saddle. It's fairly typical, by the way, to see that most points are saddles. And that's not so uncommon. But you do get the occasional nice problem where you see, a max and a min and a saddle all in one. It's not easy, but it is possible. It is possible. All right, let's do one more. One more. Find and classify the critical points for the function g of xy equals x squared y plus xy squared minus 3xy. Well, no surprises. Hopefully you're getting the pattern. Take the partial derivatives. 2xy plus y squared minus 3y. And g sub y, x squared plus 2xy, and then minus 3x. All right. Now, what do we do? Well, let's think about it. We'll set things equal to 0. Equals 0. Now, it's not so obvious how to go about doing this one. So it's not a bad idea to sort of stop and say, all right, what can we do? Well, just pick one of the terms for a second and say factor. Check to see if you can factor. And because of the symmetry, it doesn't matter. Let's look at the g sub y. Now, it looks like it's a little bit daunting, but look at all the terms a little bit closer. What do they all have in common? And they all have x. So that means we can factor. So if I pull out an x, I get x times x plus 2y minus 3 equals 0. Which means that we're in one of two cases. Either x is 0, or x plus 2y minus 3 is 0. Now let's explore the possibilities. Suppose we're in the case where x equals 0. Now we're going to take that information and go into g sub x. So when we plug that into g sub x, well, since x equals 0, what we get is y squared minus 3y equals 0, or y times y minus 3 equals 0, which says that y had better equal 0, or y had better equal 3. So we're going to get the points 0, 0, and 0, 3. So add them to our list, 0, 0, 0, 3. Now, what if x plus 2y minus 3 equals 0? Well, another way to write this is that x is equal to 3 minus 2y. So we're going to come up here, and wherever we see an x, we're going to replace it by 3 minus 2y. So 2 times 3 minus 2y times y plus y squared minus 3y is going to equal 0. And we'll multiply this out. 2 times 3 times y is 6y. 2 times minus 2y times y is minus 4y squared plus y squared minus 3y. So these combine together, that's minus 3y squared, and then we're going to get plus 3y equals 0. And if we factor out a minus 3y, we're left with minus 3y times y minus 1. So that we get that y is either 0 or y is 1. Now, suppose y is 0. What do we get for x? Well, 3 minus 2 times 0. So that says we get 3 comma 0. What if y equals 1? Well, we're going to get 3 minus 2 times 1, which says if y equals 1, then x equals 1. So we get the point 1 comma 1. So that is the find. Again, y equals 0, that becomes x equals 3, and y equals 1 becomes x equals 1. Now, phase 2, the classify. Find and classify. So, we get g, x, x. Well, it's just a single x. That's not so bad. 2y. How about g, y, y? Well, there's only a single y, 2x. How about g, x, y? Well, that would be a 2x and plus 2y and a minus 3. Okay, so there's a fair bit there. So our value for d, or rather our function for d, is 2y times 2x subtract 2x plus 2y minus 3 squared. Now we start plugging things in. So plug in 0, 0. Well, that's 0 times 0 minus negative 3 squared. Very negative, very saddly. Yeah. All right, we've got a saddle point. Plug in 0 comma 3. Well, we're going to get 6 times 0 minus, then we're going to get 0 plus 6 minus 3. So it's going to be 3 squared. Very negative. All right, more saddles. You get a saddle. You get a saddle. All of these points so far are saddles. In fact, it's going to continue, because the next one, by symmetry, if you swap x and y, you get the same thing. So if we swap x and y, it's still going to end up with a saddle. All right, one more point. Well, what could it be? So we're going to get 2 times 2 minus, then 2 plus 2 minus 3 is 1 squared. Positive. Good. Something interesting. It's a max or a min, and now we look at these values. We say, hey, fxx and fyy are both positive, so that means we are happy. So that's at a min. Min in the cross section, min at the point. A local min. Usually we don't care if you write the word local or not, but it's good to sort of reinforce the idea that what we're talking about is really a local phenomenon. What's the local behavior? And if you want absolute, again, like we said, come back next time and we'll do more. All right, see you then.